That's another thing.
Yeah, there's a technical there's a box, otherwise it won't go up.
Yeah.
Go away. Okay, it's kind of crazy.
Yeah.
Okay. Yeah, we can
Bear
get
with
started.
us.
Sure.
Okay, so welcome to the last Origins seminar talk of this semester. And today we are very happy to have Logan Pearce, ELT postdoctoral fellow at University of Michigan. Logan was a graduate student here. Logan's advisor was Jared Males. And we received a PhD in 2024. I've been bugging Logan to give talks for the last 3 years. Finally, we are very happy to have Logan here. One thing Logan worked on MegaUX, which is really great. And prior to joining Stuart, Logan actually worked on nuclear reactors, which was so cool with the Navy, and also taught in a middle school science in Texas. So she's on the way to Grand Canyon for 10-week astronomy public outreach residency there during this summer. So we are very happy to have you stop by here before you go there. So
thanks, Serena. Yes, thank you. Yeah, I'm so glad to be back here in where I love Tucson and I love Stewart and I love University of Arizona. So I'm so glad to be back here. My talk, I'm going to talk today about what my group at the University of Michigan is doing at what I say on the frontier of direct imaging of exoplanet science through JWST and reflected light. So, okay, I guess I have to click. I can't use the arrows. Briefly, I'm going to introduce exoplanet direct imaging, like so quickly. Then I'm going to talk about what we're doing with James Webb Space Telescope. And then the bulk of my talk is going to be about what I'm doing with reflected light exoplanet detections. So this one starts where they all start, with this plot of all the currently known exoplanets plotted with orbital period on the x-axis, mass or m sin I on the y-axis, color-coded by detection method. And the emphasis here is that almost all planets, the vast majority, have been discovered indirectly by observing their star and the influence they have on their star and inferring properties about the planet. For direct imaging, we are up in this regime where there are wide separation planets on giant planets and brown dwarf companions. And it looks like there's not very many, and there aren't very many that have been directly detected. But I want to emphasize that the fact that we can do this at all is remarkable. And it represents an enormous effort by a large community over a long amount of time. And so even though it looks like it's been less successful, it's incredible that we can do this at all because planets are very faint and stars are very bright. They all have been detected in self-luminous emission. So the vast majority have been detected through thermal emission. When a planet forms, gas and dust falls into the gravity well, heats up, and it radiates slowly over time. And so we are sensitive to when they're young, they're hotter, and they're therefore brighter in infrared wavelengths. A small amount have been detected through atomic emission. So again, when the gas and dust material falls into the gravity well, it can excite the gas, and that emits along atomic emission lines. There's been some success with detecting planets through their H-alpha luminosity, so looking specifically at the H-alpha line. This is WISPIT 2b, detected by a team including Laird Close over at Stewart, and then his grad student, Jialin Li, had a detection of 2-mass J1612b through their atomic emission lines. So we are sensitive to hot, young, wide, giant planet and brown dwarf companions. So this is a plot of evolutionary tracks of stars, brown dwarfs, and planets as a function of age and luminosity. So age on the x-axis and then luminosity on the y-axis, with mass decreasing towards the lower corner. And so, when they're young and they're bright and they radiate that heat away, stars eventually reach a self-sustaining point where their radiative losses are balanced by fusion. But brown dwarfs and planets never reach that self-sustaining point, and they continue to cool as they age. And so younger planets are going to be brighter and easier to detect. Here I'm overlaying, this is from Franson and Bowler 2023, overlaid pretty much all of the directly imaged companions on this plot, and we see that we're really sensitive to this hot, young regime, harder to reach the older, colder, and low mass planets. And so if we want to try to target lower mass planets and evolved planetary systems, not just young systems, if we want to do that in thermal emission, we have to go to older and therefore colder and therefore redder and fainter. So we need to go to longer wavelengths and better sensitivity. And there's one platform that's amazing at both of those things, and that's JWST. So JWST has shown remarkable sensitivity to cold planet direct imaging. And my group at Michigan has a lot of people that are exploiting this capability. If you were here a few months ago, Rachel Bowens-Rubin was here. She's my colleague and roommate. They recently had a paper showing that MIRI is exceptionally sensitive to really cold planets in the nearest systems and will catch planets that NIRCam, which is a shorter wavelength instrument on JWST, will miss. So this plot shows distance to a system versus the coldest planet that MIRI, or that can be detectable at 3 sigma, and with NIRCam in blue and MIRI in red. And in this red shaded region here, these are planets that would be detected by MIRI but missed by NIRCam. And zooming in on this lower corner here, we can see that in the closest systems, MIRI is potentially sensitive to planets as cold as the planets in our own solar system. And the reason why MIRI will catch ones that NIRCam might miss is due to clouds. So this is a plot from their paper showing a clear models of a Saturn-like planet in the gray dash, and the purple and solid are cloudy models. And the solid line, the horizontal bars, show the sensitivity limit for the different filters. So for NIRCam 444 filters, so that's 4 microns, the only model that is above the sensitivity limit is the clear model, and the cloudy ones are too faint. Whereas if you go out to longer wavelengths, this is the MIRI 21 micron filter, they're all accessible to, they're all above the sensitivity limit for MIRI. So a lot of folks have been using NIRCam, but our group is really advocating for that we should be focusing on MIRI for these cold planets. And MIRI has been successful. This is a recent discovery by Elizabeth Matthews and her team in 2024 of EPS-ND-AB in MIRI. It's EPS-ND-AB is a 6 Jupiter mass, 275 Kelvin, 3.5 gigayears. And this is the 10 micron and 15 micron filter. And if you're not used to looking at exoplanet direct imaging, you might not realize just how shocking it is to actually see this strong of a signal for a cold, directly imaged planet. Seeing the actual like airy pattern of the point spread function is insane. So this is a remarkable result. The EPS-ND, the star has been subtracted and it's behind here. And so this is the planet. And recently we, an undergrad working with my group, Matson Garza, was able to take the EPS-ND-AB planet signal, use direct imaging point spread function subtraction methods to subtract the planet signal and look for moons or binary planets. And he was able to rule out moons of Jupiter mass and higher around EPS-ND-AB using point spread function subtraction techniques on a planet instead of a star, which is really cool. And so our team at Michigan has several programs looking for planets in nearby systems. Rachel is the PI of a Cycle 3 program called Cool Kids on the Block, surveying 6 nearby stars, and a Cycle 4 program surveying 150 nearby stars. I had a proposal that was not accepted for Cycle 5, but to look for outer cold gas giant planets around systems with known habitable zone rocky planets. So I think that's a great science case, and so I'll be continuing to try to push that one. And these are starting to show some results. So I will tease you with a preliminary result from Hoth, this of a 3-color image of a possible 125 Kelvin companion around a star. So stay tuned for results from Cool Kids and Hoth because they are coming out now. Another way to use JWST to access cold planets is through white dwarfs planets. So white dwarfs are so hot that when you go out to the long wavelengths of MIRI, the contrast between the white dwarf and a planet is like 100 or 1,000. It's like 10 to the minus 2, 10 to the minus 3. So really, really low contrast. And it's such that the planet produces a significant IR excess in these, even if you can't resolve it, in these long wavelengths. Marianne Limbach has a program called MEOW, which is M-dwarf exoplanets orbiting white dwarfs. Yeah. Where they detected the known white dwarf planet WD 1856b, which is 185 Kelvin in infrared excess. So this is MIRI wavelengths on the bottom and or on the x-axis, and then planet star contrast on the y-axis. And the planet is hot enough that it produces a significant excess in IR wavelengths compared to models with no planet present, which is the blue. And they made a new discovery of 250 Kelvin planet WD 0310b, which is 3 Jupiter masses, and they were able to show that it's most likely a planet and not like a hot disk, a debris disk. So I have a program from cycle 4 of JWST that combines both of these detection methods to look for planets around Sirius B and Procyon B, which are 2 nearby hot white dwarfs. So this figure is from my proposals saying where I think we could get with separation and the radius of the planet. We could detect for at 5 sigma, which is blue, and 3 sigma, which is purple. So out in this regime, we would use direct imaging techniques to look for cold planets using 18 and 21 microns. And then interior to what we can resolve with direct imaging techniques, we'll use IR-XS to look for infrared excess in 25.5 micron filter. This program was just observed. I have not got any results yet, so stand by. But in case you want to see what it looks like if you point the world's most powerful telescope at the brightest star in the sky, it looks like this. This is my data. This is Sirius A completely blowing everything out. And Sirius B is right here, if you can kind of see it. It is right there, and it's right here. And so I need to look at this data and get results, so stand by for that. But it does seem that MIRI survived being blasted by the brightest star in the sky.
Is this allowed?
Yeah, I was going to ask, is it allowed?
That seems.
We did it, yeah.
How long did the latency last?
Well, that's a great point, because let me point you to a paper by Alicia Vassan, an undergrad in our group, who looked at MIRI persistence and found that it decays away after about 10 hours. So
10 hours.
nobody could use MIRI for about a day after we used it, and
Oh
it
my
was
gosh.
it's fine. The JWST team, they made sure everything was working and wouldn't get broken. Did you have a question, Josh?
Oh, yeah, just because I was also curious regarding the brightness, because I remember, I think from the direct imaging paper with JWST on Alpha Cen, I think they were saying that it was too bright to point at it directly. So
Well, it's too bright to like guide off of it, or to like
Okay.
use it as pointing. So we had to actually do like pointing offsets to get it in the right spot. Yeah.
Okay.
And we also aren't using the chronograph. So the Alpha Cen program was looking at Alpha Cen.
Yeah.
And so they put a coronagraph around it, but I'm looking at Sirius B. So I actually don't care about A. So I didn't use a chronograph.
Okay.
Yeah, A is just a nuisance. We're gonna subtract it away.
Okay.
And B too, but anyway, so it's similar but slightly different. Great question, yeah. We used what they had done as a guide to help us figure out how to do this correctly.
Okay.
Yeah.
So we know whom to ask if you have to observe something that is very, very bright.
Ask Marianne, because she's way more of an expert than I am at that. I leaned on her heavily. She's a JWST expert. Okay, so that's JWST, but what about habitable zone rocky planets? So what if we want to go into this low mass, potentially habitable regime? So a quick technical break. When you're looking through space or in adaptive optics corrected images from the ground, we're in diffraction limited imaging regime, which means that the thing that sets the point spread function, or how big your star is in your image, is set by the wave nature of light and the telescope, and it's not set by the atmosphere. And this means that the fundamental size scale goes as the ratio of wavelength to primary mirror diameter. So if you have a longer wavelength, your point spread function is larger. Smaller diameter, point spread function is larger. And this matters because the ability to resolve 2 point sources, like a planet around a star, is kind of goes kind of like 2 lambda over d. So things that are closer than that are not going to be resolvable. So to get in closer, we need a large primary or a shorter wavelength or both. And this means that the habitable zone of nearby stars is inaccessible to JWST, for example. We could kind of get there with Sirius B just because it's so hot and the habitable zone is so far away. We think that's pretty much the only star that JWST can get close to the habitable zone. But if you switch to visible wavelengths, wavelength lambda over d goes down. Now the brightness of the planet is decoupled from age. And so we can look at older, more evolved systems. And we can look at the light that the planet reflects from the star and then imprints the planet's spectral features on the star spectrum. And then we can try to access habitable zones in evolved rocky planets. And so this has not been done. There have been no directly imaged planets with reflected light. But upcoming technology is going to enable this for the first time. And if we can probe in the visible through reflected light, we can start to push into this regime in here where we know there are planets already that we can go after with reflected light. Reflected light also probes a different atmosphere regime than thermal emission. So with thermal emission, you're looking at the photons that have come up through the clouds and the atmosphere. Whereas with reflected light, you're looking at the light that has scattered off of some level of the atmosphere. So you're actually probing 2 different regimes. And ideally, if you could look at one planet in both, you could really get a handle on the energy budget of the planet, which is something that Michael Meyer's group at Michigan is really interested in. And you can see here in this image of Jupiter in thermal emission, where you have this really bright band, for example, where the clouds are thin. It's really bright in thermal emission, but that same regime where the clouds are thin is going to be darker in reflected light. There has been some work by Stewart alum Kevin Hardegree-Ullman, who showed that O2 and other biosignatures detection is really only available to direct spectroscopy. So he had a series of papers looking at in the most optimistic transit spectroscopy case, to get one Earth-like detection of an O2 concentration, it would take a survey of about 100 years in the most optimistic cases. Whereas with an ELT and spectroscopy, you could get on the order of 10 in 1 year, assuming that they're there, of course, which is an assumption. So it's promising, it's great technology. It's one of the ways forward for direct imaging and exoplanet characterization, but it's very hard because contrasts are high. This is a classic illustration from Kate Follett's review paper in 2023. If you think of the star like a lighthouse light, then the reflected light contrast, that trying to see Jupiter in reflected light is something on the order of 10 to the minus 9 ratio. So this is 1 billion times fainter than the host star, which is like bioluminescent algae compared to a lighthouse light. So this is the kind of contrast that we're talking about here. And they're also very close. So if you look at an Earth-like planet and an Earth-like separation to a sun-like star, that's a separation of about 100 milliarcseconds, which is like trying to see the bow and the stern of a cruise ship on the moon. So bioluminescent algae next to a lighthouse, the size of a cruise ship on the moon. That's what we're talking about here. And a lot of work is needed to get to that point technologically. So this is a plot from Vanessa Bailey showing this is hundreds of known exoplanets and reflected light contrast, separation on the x-axis, contrast on the y-axis, and then some thermal emission planets, and overlaid contrast curves for current technology and past technology. So the way you read a contrast curve is if it's above and to the right, it's detectable, below and to the left, it is not detectable. And so you can see there's a large gap here that needs to be bridged between technology and reflected light planets. But upcoming technology is expected to bridge that gap. So the Nancy Grace Roman telescope has the coronagraph instrument, or CGI, and it's expected to deliver some of the first reflected light exoplanet detections. This is that same plot, but now with some of the Roman contrast curves overlaid, predicted contrast curves. And you can see that we're starting to get down into that regime where some of the brightest gas giant planets are going to be detectable in reflected light. So we're expecting Roman to be able to detect a few reflected light planets. And then the Habitable Worlds Observatory, which is the follow-on Space Telescope program, is expected to deliver population-level reflected light exoplanet detections. Ground-based platforms are complementary to space-based platforms. So with space, like Roman, HWO, and the Lazuli Space Telescope, you might have a lower background because it's in space, but you have smaller primary. With ground-based, if we have maybe a higher background level, but we have a larger primary, we can get in closer. And all three extremely large telescopes, or ELTs, that are upcoming all have instruments designed for this science case. The ELT has the PCS instrument, which is, so Michigan is a partner in some of the ELT instruments. That's the European Extremely Large Telescope, by the way. And so I've been able to participate in a lot of the conversations on the development of ELT PCS, which is currently ongoing. It's planned to be a second generation instrument. The ELT itself is pretty well along being built. It's pretty cool. But the instrument for the science case is a little further behind. Here at home, we have the GMAG-AOX instrument for the Giant Magellan Telescope, which is PI'd by Jared Males here at Arizona. And it was just recently confirmed as a first generation instrument for GMT. And then TMT has PSI, and I don't know the status of that instrument. And we also have the MAG-AOX instrument here at home, which is a extreme adaptive optics instrument for this science case on the 6.5 meter Magellan Clay telescope in Chile. And they are just now transitioning into reflected light imaging campaign mode, which is a different mode of operation than they have been interested in. But this instrument is designed and is operating as a technology development platform for this science case. It's very hard technologically. Major technological advancements need to happen. This slide right here could be its own 1-hour talk. So if you're interested in this stuff, I would like to direct you to the MAG-AOX team. But in addition to being hard technologically, it's also extremely hard observationally. And so that's what I'm interested in, and that's why I'm going to spend a few minutes talking about some of the challenges to actually making these detections and how we're really not there yet from the observational side either. So uninformed searches, meaning just staring at a star and hoping you detect something, is really infeasible because of the high contrast involved and planet visibility. And so we need to go after planets that we think are there and we can know something about ahead of time. So this is a similar plot to the Vanessa Bailey plot that I showed of hundreds of the nearest known exoplanets in their reflected light flux ratio, with now some of the ground-based contrast curves overlaid. So here's the inner edge of the most optimistic Roman and Lazuli curves, and then GMAG-AOX target and goal, and then PCS's most optimistic contrast curve, and then HWO is, I don't know, way down there. Who knows what's going to actually happen with that. But you can see that even if we can't get as deep, we can definitely get in closer where there are tons of planets that we could potentially go after for this science case. But most of these are RV detected, which means I had to make a lot of assumptions to make this plot. We don't know, radial velocity only gets you the minimum mass, not the true mass of the planet. And so I made some assumptions. And then inclination is also not known with radial velocity only. And so I had to make some assumptions about separation. There's not quite enough information with just radial velocity. The planet's detectability as a function of time depends on its orbit. So this is an excellent illustration by Keithley 2021. So if we have a coronagraph that has a region that is only, the detectability is only this white donut. So there's an inner working angle and an outer working angle. Those are the gray areas where the planet is not accessible. So in this hypothetical example, this dotted area is where the planet is too faint because it's at like a crescent phase to be detectable. In the red area is where the planet will move into an inaccessible region in a faster time than it takes to observe the planet. And so this planet in this example would only be detectable when it is here in this part of the orbit, which you have. So in order to detect this planet, you have to know when it's going to be here and for how long. So it means you have to know the orbit really well to be able to do that. It could be even worse from some of the most promising coronagraph designs that can carve regions of really high contrast. Like this is called electric field conjugation, and it carves this region here. This is a simulation of EFC, but it carves this region here where it can get to contrast as high as 10 to the minus 9 or 10 to the minus 10, which is what we need to get to this, to get to these tough detections. But it only carves it in this one region. And so you'd like to be able to know when the planet can be in that region before you go to try to image it. Otherwise, you're wasting time imaging a bunch of times and orientations and hoping the planet is in there in some of them. Something that direct imagers have not had to worry about until now is that planet's orbit. And in the case where we're trying to image something so faint, we might need to observe it for hours. It's going to move a lot during that time just to get a detection. So this is a plot from Jared's paper showing contrast in the habitable zone as a function of planet size and star spectral type. And so in these areas where the contrast in the habitable zone is highest, so that's the most promising targets for finding habitable zone planets, the habitable zone is like 0.3 AU, 0.1 AU. So the planet's going to move a lot when it's that close to the star. For example, Proxima Centauri B has a period of 12 days. If we need to observe it for 100 hours to get enough signal, it's going to move a lot during that time. And we need to know the orbit to be able to deorbit and stack and add the signal to make a detection. But if we don't know the orbit very well, which we don't for ProxSenB, we have to try a whole bunch of orbits, and it gets really challenging. And ProxSenB is actually one of the best cases. Well, I'll talk about that in a minute. Anyway, there's a degeneracy between phase and radius. So a full phase planet, small planet, can have the same flux as a crescent phase giant planet. So to break this, you need to either have a precise orbit or a precise radius. There's also an issue that, again, thermal emission hasn't had to think about, in that if you don't have velocity information in all three dimensions, there's a degeneracy between the nodes of the orbit. So where the planet transitions from being behind the plane of the sky to in front of the plane of the sky. It doesn't matter unless you care about phase, which I do care about. So in this example, this is the exact same orbit, but the ascending and descending node have shifted. And so the planet being here at a gibbous phase in one, which is the brightest, or here at a crescent phase, which is the faintest, depends on knowing where the nodes are, which you can only get from having velocity in the plane of the sky and radial velocity to break that degeneracy. There's a degeneracy between radius and separation. So this is a equation for contrast, and it depends on the ratio between the planet radius and the separation. So this is an illustration from Salvador 2024 showing distance and radius. And if you don't have any other constraints, any detection that you make could be in this blue region here. So a giant planet far away can have the same flux as a small planet close in. To narrow down the radius more tightly, you need orbit information and ideally a tight mass constraint too, which you can't get from just like an indirect method like radial velocity. Additionally, rings and moons will confuse your interpretation. So there are times where Saturn's rings are way brighter than Saturn itself. There are even cases where Triton is brighter than Neptune. And so these can really confuse your interpretation if you do make a detection. I'm working with an undergrad, Lizzie Lane, who has a paper coming out very soon showing how we can use phase curve observations to break this degeneracy. So if you can observe the object in multiple points of an orbit, a ringed planet will have a different shape than a ringless planet, and you can break the degeneracy that way, but that involves observing it lots of times. debris disks and exozodiacal light can be greater than the planet's contrast. This is a simulation of an Earth-like system with an Earth-like zodiacal dust pumped through a simulated coronagraph to produce a simulated image where the zodiacal light, so this is just the dust around the near the location of Earth, is brighter than, is at 10 to the minus 6, so it's brighter than the planet. There was recently a paper showing that we need to know mass within 10%, even to just be able to find biosignatures from a spectrum. So without knowing the mass of the planet really well, they were unable to pull out the Earth biosignatures from a simulated reflected spectrum. And then literally on Friday, a couple days ago, there was a paper showing that even that different climate states of the same atmosphere can confuse your interpretation of things like oxygen or water. So this is showing albedo spectrum of no clouds and clouds for a Earth-like exoplanet with global ice, an ice cap, an ice belt, or no ice. And these all have the same O2 compositions, but the size of the O2 feature and the equivalent width of the feature changes based on just on the ice state, or the climate state of the planet. So even just knowing the atmosphere composition isn't enough for predicting the atmosphere. It can confuse the climate state can confuse the atmosphere interpretation. Okay, so to officially observe these planets, we need to know and interpret our observations. We need things like 3D velocity, tightly constrained orbital parameters, true mass. We need to be able to observe it over phase curves. We need to have an idea of the dust level, the temperature in the system, and these are enormous problems. There's a little bit of hope with Gaia DR4 and DR5, which will provide 3D orbit information for giant planets. So this is a simulation by Lammers and Wynn 2026, simulating the planets that Gaia DR4, which is coming out in December 2nd, is expected to find, is red, and DR5 is black. Translating that into this plot with DR4 in orange and DR5 in gray. There's a lot of potential targets here with three-dimensional velocity information and well-constrained orbits. So there's some promise here for gas giant planets. Unfortunately, these are all super Jupiters and Jupiters that Gaia will be sensitive to. Rocky planets are harder, much harder. M dwarfs are active, and the planet signals are small. Proxen B has been studied for a decade, and the orbital constraints are not very tight on that one, even though it's been observed to death because of these fundamental issues. And so I don't know what the answer is for those. We'll see. So I'm working on tools for the community to try to plan for these observations. So if we want to know the exposure time and observability of a planet, I've broken it down into these kind of regimes of things that we need to think about and know in order to make those predictions. Right now I'm focusing on the atmosphere part. So contrast, planet-star contrast depends on, as we said, the ratio between radius and separation and the viewing phase. It also depends on the albedo as a function of wavelength. And so that means that we need some atmosphere forward models in order to be able to try to plan for and predict, plan for observations and then try to understand observations if we ever make them. And so this depends on the chemistry, the star, the gravity, clouds, scattering, all kinds of stuff. And so I've been working on building the Reflectex model grid, which is a grid of gas giant planets from a Neptune analog up to a super Jupiter analog for 5 different star types, bunch of different temperatures, C to O ratio, clouds, cloud parameters for a total of 36,000 total forward model spectra. It's built on Picasso, which is a radiative transfer code, and Virga, which is a cloud modeling code. This grid is available in a few days. It's nearly almost done, and the paper will be out soon. This is one example of some of the spectra in the model grid. This is a Jupiter-like planet at 200 Kelvin. The zoom is covering my slide. With water and sulfur haze clouds. And the different colors are different cloud parameters. So FSET is a sedimentation efficiency. A low sedimentation efficiency means that you get thick, fluffy clouds. High sedimentation efficiency means you get thinner clouds. And we can see that if you have big, thick, fluffy clouds, it's nice and bright, especially out here at J and H band, which is these filters. But you wash out the spectral features. And so it might be easier to detect, but harder to characterize. This is the same planet, but now in a color magnitude diagram. So this is I minus H color versus J contrast. Viewed as a phase curve, so 3 different phases. And the different colors are different cloud parameters. And so we can see that different cloud parameters produce different behavior as a function of phase in color magnitude space. So even if before we even get a spectrum, we can just get broadband photometry, we can start to place some limits on that atmosphere of the planet. So that's the gas giant part. I am also currently trying to collect experts in subneptunes and rocky planets, because I'm not interested in making those myself. There are people who are way better at that than me. And so I would like to work with them to have forward model spectra for what we might find for these type of planets. And then I'm interested in trying to build a tool incorporating all the rest of these things towards this science case to help prepare for the upcoming observations. Before I finish, which I'm finishing kind of early, that's fine. I just wanted to plug why I'm here this week. I'm on my way to the Grand Canyon. I am one of the astronomer in residence this summer for 10 weeks, where I am going to be living at the Grand Canyon on the rim, interacting with the public, giving talks, public talks on dark sky advocacy and other interesting science astronomy that's interesting to the public. And I'm going to produce some infographics and stuff while I'm up there. And so you can follow along on my website. I'm going to try to blog what I'm doing. And there's an event schedule if you're planning on visiting the Grand Canyon this summer. Come say hi. But yeah, so with that, I will leave up my summary and I'll take questions.
Have any questions in the room or
Yeah.
chat?
So I have not been following the technological development of GMT instrumentation and the other giant ones, but what are the prospects? It sounds like we're in good shape to be able to image for the high contrast imaging to work, but what are the prospects of getting spectrum behind that?
Yeah, I mean, so
Because that's what we
GMAG
really want, right? We want
yeah.
GMAG-AO or whatever
GMAG
with a spectrograph behind it.
Yeah, it will have spectrograph. And I don't, PCS also will as well. That's all up in the air with design. GMAG-AOX is a lot further along on the design than PCS, but both are going to have IFUs. Absolutely.
You know what resolution?
That's the open question. That's why we need these models and this kind of tools, because we haven't figured that out yet. A lot of people are working on that, but it's not decided. But I've been focusing on broadband photometry more because the first step is making these detections and imaging, right? There's so few photons that trying to split them out into a spectrum, like first, you know what I mean? Like, I don't know. If all we can get is a broadband photometry, what can we do with that?
So what are there resolutions that are being discussed?
I can't off the top of my head. I haven't been part of those conversations. There's actually a team at Chicago who is starting to think about figuring out the optimum resolution for GMAG-AOX. And then I've not been part of the conversations of that for PCS.
Is that Jacob's team? Or is it somebody else?
No, it's Jason. Yeah.
So you, at the end, kind of got to albedo, but it didn't appear as like a nuisance parameter, say in the y-axis of your reflectance curves.
Yeah.
So what kind, I mean, you have 35,000 giant planet models. What are the ranges of albedos you've been getting?
I don't know. I just messed something up. I'm sorry. Where's share? Yeah, I was trying to find the screen.
Oh, okay.
All my open screens, I was trying to find the right one. Okay, I'm sorry, what,
What kind of albedos are you getting, right? Because in principle, that number goes from 0 to 1, which could take your contrast from what you showed to infinity, negative.
yeah.
So which, I'm assuming it's non-zero, so, but I don't know, I don't have any sense of like what the range is for these models.
Yeah, so for this is a simple Lambertian contrast. I made a lot of assumptions for for a hand wavy plot here as a starting point. This is an example of, oh, so this is contrast. The answer is I have a lot of plots of that, but I don't have them available to show right away. But the, like, in this particular example, in the cloudless case, the albedo goes from like 0.7 to like 0 down here. So the paper is going to come out soon. It will be in there. But a lot of different ones, 36,000 spectra of all different kinds.
But the bottom line is that, I guess from this figure alone, you would say that for plausible cloud models, the albedo does indeed go from 10 to the -3 to order unity or something like that.
Yeah, I wouldn't say 1, but
Points at order unity.
Yeah,
points at-
something like that.
I see it's not 1.
But you know, like ice and stuff can get to 1.
Yeah.
So that's not implausible. But not for the gas giants. Yeah.
Any other questions?
Yeah.
Yes.
What do you think about the reflected light observation for white dwarf and planet system?
For white dwarfs,
Planet system.
well, I haven't looked at that specifically. White dwarfs are hotter.
They might be fainter and
Yeah.
less look.
I haven't done any modeling work with white dwarfs yet. I have to think about that. Good question. Thank you. Yeah. Caitlin, yeah.
So the Sirius image,
Yeah.
it looks like absurd. Like, I mean, I'm trying to be very, like, it looks like it's an absurd, like, to even recover Sirius, like, maybe if you told me your goal was to see Sirius B, I'd be like, I guess you can do that.
Well, it's right there. You can see it.
Right, but if you're trying to do something around Sirius B, like, what is it? How did you demonstrate that it was at all plausible that you could do this signal subtraction?
I used other Miri data as like a, and then scaled it as like a proxy. Yeah. But coming from a ground-based imaging background here, and starting working with JWST data, I was able to get background limited all the way in like 4 images, because JWST is so absurdly stable. It's crazy. So I have high confidence that I'll be able to subtract this away, even though it looks ridiculous.
Is it saturated?
Yeah, see all this?
I
This
bet.
is saturated even out here.
But I guess that's kind of I don't understand how you can subtract if it's saturated.
Yeah, how's there anything left in the ADC?
Well, I'm not interested in this part.
But even.
I'm out here.
Even on the side with
Yeah,
the
like there's
spikes,
things going towards.
they're all
me, but yeah.
saturated.
Yeah, but that's not, like, this is not saturated. The speckle's not saturated,
Okay, that's kind of what I was asking.
right? It's like saturated in
Yeah.
here.
Because the contrast
But-
as displayed here.
So
it
it's
can be
not
seen.
saturated, and I did a lot of work to show that Sirius B, or that Sirius A is not too bright at the separation of Sirius B to be able to do this. So it's not saturated in the regime that I care about.
Okay.
But yes, it is ridiculous.
I mean, if you.
That's why I made this logo for my program. Lol. Yeah.
Yeah, so if it's a spectroscopy, it's, in a way, it's easy to subtract A star. I mean, this is like Sirius A, is white dwarf, you can subtract that really well. But then it's for the imaging.
Yeah, well, I got reference stars, yeah. It's a reference star subtraction, yeah.
If you can zoom in only that area,
Which is the area I care about.
yeah, I
Oh,
don't
right
know how
now?
you would see it. Whether you could only see, really zoom in.
That's as far as it's letting me go.
Okay.
Live action.
Yeah,
Yeah.
that's it.
Right at the
Amazing.
limit, I would say.
Yeah.
I just feel like you erase better and you would use a coronagraph, knowing what you know about coronagraphs.
So the proposal was for a coronagraph. We had to submit a detailed change request to change to imaging. And the reason is that I'm not interested in Series A. If I was looking around Series A, I would need a chronograph.
But you're not worried
But
about any of the diffraction spike artifacts? Okay.
Nope. At the separation of Series B, Series A does not influence it enough that the backgrounds for MIRI coronography is higher than imaging. And we think we're background limited at this separation. And so we want the lower background. And so we switched to imaging. We had to go through a whole procedure because the proposal was for the chronograph.
So not using the coronagraph allowed you for the lower background?
Right.
Okay.
Because we think we are expect to be background limited here.
That's a better argument than Larry Gibbs for not using a coronagraph.
I've pretty much never used a chronograph.
This is the craziest JWST image I've seen, I think.
Yeah, that's why I wanted to show it because I literally just got it. Like the observations just happened, and so that's why I was like, I don't have any results, but I can show you what a crazy image looks like. Yeah.
I have a question
Yeah.
about the grid of models that you generated.
Mhm.
So maybe I missed, but in your models, do you cover the region of the younger objects, like for example, the giant planet forming giant planets in the basis or something?
No, so one of the limitations of my model grid is that I'm only considering reflected light, so I don't care about age. But there are cases where the planet's thermal emission does matter. And so that's not captured in my models. And that's something I'm planning to incorporate into the next generation of models.
Do you have any other questions in the room?
Or online.
For the online audience, if you have a question, please raise your hand, or you can just type your questions in the chat and we can say it.
Otherwise, yeah, can you say, then we have a Logan here on Thursday?
Yeah.
Yeah, except tomorrow, Logan's available. There is if you go to the email, there is a click here button. You'll receive the spreadsheet to sign up.
And it's wide open right now, so.
Yeah. So if we have no other questions, let's thank our speaker again.
And then we'll meet in the fourth semester, and there are already requests